Hi, I'm Charles, and welcome to part 25 of the OpenSCAD video series. In this part, we're going to be talking about pointing, which is getting certain objects to point at certain points in space. So essentially, this green cone here, we want to point at this red point here. Let's get started. So, to start, I've put together a little demo to demonstrate what this should look like. So, we have this green cone here, and we have this red point here. And we want this green cone to point at the red point. And so we can see that it's already doing this because I've already made the demo, but this should help explain how it's done. So there are essentially two angles that we rotate around to get the rotation that we want to point at the point. So let's start with a bit of implementation. So we'll create the cylinder, it's a cone, but we use cylinder to make it. Let's say 2. Equals 0. Oops. Center is true, and the FN value equals 100. And I forgot to add the height. H equals 3. Maybe we'll say 5. Okay. So there is our cone, and we wanted to get it to point at some arbitrary point in space. So let's make that point in space. We'll call this point point. And let's say it's at 3, 4, 5. Actually, I need to do something to show it. So okay, so let's say we have our cone here, and we have our point that's over here, and we want this cone to point at this point, like what's happening in this demo over here. So I'm going to do something, and it will become clear, I hope, why I'm doing this from the demo over here. Just because I think it's easier to conceptualize in terms of angles. So I'm going to rotate this this cone around the y-axis so that it's pointing in the positive x direction. So this is the x-axis. We want to rotate the point of the cone to be pointing in the x-axis, to be pointing towards the positive x-axis. So I'm going to rotate the cylinder. We want to rotate it around the y-axis, and we want to rotate it 90 degrees, I believe. Yes. Positive 90 degrees. And that gets us pointing in this direction towards the positive x-axis. So that's kind of where we start out here. So now moving back to the demo, now that we have our cone pointing in the positive x direction, essentially what we need to do is apply 2 rotations to it. So the first thing that we do is apply this rotation, which is from the xy plane towards the z axis. So in this case, it would just be rotating along the y-axis again. We want to rotate this point towards or away. Well, I guess either way it's towards the z-axis, but we want to rotate this either up or down. And so, as we can see here, it's rotated by this angle alpha. If we're looking at it kind of from side on without seeing theta. Theta is important too. Just a second. So the cone is rotated up by alpha, and alpha is the angle between, I guess, this line that points from the origin to the point, which is directly from the origin to the point, and the xy plane. So yeah, that's that. The next thing we want to do is, so because when we rotate this, it's going to be a line. Let me just give a quick example. If I were to rotate this, along the y-axis, around the y-axis, sorry, negative 45 degrees. So it's pointing up, but it's still stuck on the xz plane. And that's, it's a good start, but we also need it to be pointing to any point in space. And if it's stuck along the xz plane, it won't be pointing to any point in space. So we need this second angle, theta, to rotate it toward the point. So let me just get rid of this. I'm going to change this into a module. Point to location. So I'm going to take this out, put it in here. I'm going to use the children identifier, which means the child objects of this module. So if we go back, it just goes back here, but then we're going to use the module so that it's easier, so that it's easy to use on a bunch of different objects. And the location should be point. And what we've essentially just done in the module is rotated it 90 degrees about the y-axis, which is what we have here. Okay, so now we have this in a module. That's good. So we want to do these two rotations, but to figure out the angles that we need to rotate by, we need information. We need to figure out what they are, and so we need some equations to do that. And so some important things to note that are going to be in these equations are these variables here. So we have x, which is the x-coordinate of the point, y, which is the y-coordinate of the point, and z, which is the z-coordinate of the point. And so another important value is going to be r, which sort of stands for radius, but I've just called it r. It's this line from the origin to the, if we neglected the z-coordinate and just considered the xy coordinate and made a triangle, it is the line from the origin to the xy coordinate, the xy portion of the coordinate. And we need this. This line from the origin to the xyz coordinate is not as important for calculating the angles. I think it could be used, but it's not necessary. So I'm going to talk about the equations now. But before I do that, I just wanted to give a small demo of what's going on here. So this point is going to move. I've animated it so that it will move, and you can see that the green cone will follow it wherever it goes. So as you can see, the red point moves around, and theta and alpha change to accommodate where the point is so that the cone can point to it. Yeah, and that's pretty much it. That's what the demo does right now. Take this back to 0. There we go. So yeah, let's talk about some equations. So here are the equations. We're going to be using something called the arctan function. We'll actually be using the arctan2 function, but I'll talk about that in a second. So to do trigonometry, or to calculate the angles, we need trigonometry. So because we know that these are right angle triangles, we can calculate the angles from the relationships between the x, y, and z coordinates as well as r. So hopefully there is some knowledge of trigonometry going into this. It should be fairly easy to refresh, but I'm also just giving the equations and we're doing the whole thing. So you can just copy it down if you need to. So we start by saying we know that the tangent of theta is equivalent to y over x. And so if we take the inverse of this to this side, we can see that theta is equivalent to the arctangent of y over x. And what we're actually going to be doing is using this function a tan 2, which is arctangent 2. And I'm just going to talk about that briefly because it's important to use arctan 2. So this is the tangent function. For pi, like going from 0 to, I suppose, pi over 2, I think it is. And yeah, there's pi. So pi over 2 is an asymptote, and this is the general tangent function. We don't need to worry about that. The arctan function essentially just takes one of them and turns all values from negative infinity to infinity and squashes them between negative pi over 2 and pi over 2. Yeah, pretty sure. Yep. So, cool. These are the functions. And then we get to a tan 2, and we use a tan 2. There's a Wikipedia page because there's a little bit of ambiguity when using if you have a positive or negative number, the arctangent function can give you a bit of ambiguity, which is bad if you want something to be pointing in a particular direction. For simpler things, it's not an issue, but for what we're doing, it's important that we use a tan 2. Yeah, you can read the Wikipedia page if you're interested, but I won't be going into it here. So we went through the theta function. The function for theta, we're going to be using arctan yx. And so now for alpha, this angle up here, the vertical angle, we know that the tangent of alpha will be equal to z over r, because that's how the tangent is defined, opposite over adjacent. And again, we can take the inverse and say alpha is equal to arctan z over r, and again, we switch that to a tan 2, or arctangent 2. And so the numerator goes on the left side and the denominator goes on the right side. So one other thing that's important is we need to be able to calculate r, because we don't have that from the coordinates, we don't know that already. So there's one more formula for r, and so r, this distance from here to here, is equivalent to the square root of the x component squared plus the y component squared. And in terms of OpenSCAD, we can just say the norm of xy. So this is a little this notation is slightly incorrect, but you'll see in the when we write it out in the program. Okay, so we should get started. Okay, so let's start out by calculating. Well, first let's define the coordinates. Let's say x is equal to location 0. So just writing out all the coordinates. Y is equal to location 1, and z is equal to location 2. Okay, no problems, cool. So now, so an important thing to note is the alpha rotation is applied first. So we rotate by alpha and then by theta. So it's not theta first and then alpha because it wouldn't work exactly right. So we rotate by alpha first and then theta. So let's calculate the alpha angle. So as I said before, we need r. So r is equal to the norm, and this is where my notation is slightly off here. It is, instead of this, it is x, y, 0, because we just want the distance of xy to the xy component. Okay, so now that we have r, we want to calculate alpha. So let's calculate alpha. Alpha is equal to a tan 2 z r. So now we can rotate our object, and because generally this is how I like to think about rotations in OpenSCAD. If you are looking from the positive direction to your object, so right now let's say I'm looking at from the positive y direction. So this is the y-axis. Here's my object. We know that a positive rotation is going to go counterclockwise. So it's going to go this way. So what we want is the object to go this way, so we know that we need a negative rotation. So same with the z-axis, we know that if there's a rotation, a positive rotation, it's going to go counterclockwise. And same with the x. So we want this to point up. So we're going to rotate it by alpha. Negative alpha, actually. Yeah, negative alpha. And I get an error wide. Oh, there's no r. Our little r doesn't exist. So we need big R. There we go. Okay. And it's kind of hard to tell if it looks right or not. It is sort of, it is right, but it just, so, okay, let me just, if I brought this to the XZ plane, so if I give it 0 y value, it will be correct. So as we can see, it clearly points to the object now on the XZ plane because we don't need any theta rotation in this case. So it clearly points at it, and I can even add the line to demonstrate it. Okay, it's a bit small, 7.5. But yeah, as we can see, this is sort of a useful trick, but the point of this cone is completely encased in this, and it should be more or less however small I were to make the size of these cubes. It should the tip of the cone should be fully encased inside, and it's pointing at the center of the cube. The cube again is kind of it's kind of big. Say 1/4. There we go. It's smaller now. There we go. So it's easy to see that the point is the center of this cube here, and our object, which is our cone, is pointing at it. And that's so we've got half the battle, because it's just constrained to the XZ plane right now, but we want to be able to point it to any point in space, so we need to work in theta. So move this back to being 4. And so now it's not aligned, but it is in a way, sort of, but that doesn't matter right now. Okay, so next we want to calculate theta. So again, we go to our equations, and theta is equal to the arctangent of yx. Now that we've got that, so now we need to rotate around the z-axis. So we rotate by theta around the z-axis. Let's go back just so we can see that. So alpha is that is the rotation in the xy plane that moves it kind of up and down, and theta moves it around the z-axis. Yeah, so we're gonna rotate by theta, and it can be positive theta because we want that counterclockwise rotation, and boom, there we go. I'm glad that worked the first time. So yeah, now it points at any point, and that's pretty much the basis for this whole thing, and it's a really useful operation. So something that we can do, I'm gonna bring this to the full screen now. Okay. So now that we have this, I think I can have a little bit of fun with it. So one trick is that if this cone is not necessarily on the origin like it is here conveniently, it could be anywhere in space. But let's say the point is the same, but this cone is somewhere off in space, but we still want it to point to this point. So essentially, what we do, we need to specify the position of the cylinder, or the cone. So we'll say cone position. Let's say -7, -3, and 10. So if we just wait. If we just translate it, it's not good. So I should actually put this here too, just so that we can see from the center what it's pointing at. So that's not good. That now we've sort of broken it, but there's an easy way to fix this. Essentially what we do, so we're pointing at the point. Essentially what we have to do is just subtract the cone position from the point. So if we subtract the cone position, essentially what that does, that relatively puts the cone here at the origin, and moves this relative to what the cone would have done if it had been moved to the origin. So the point ends up in space somewhere over here, and then it goes back. So we have cone position, and there we go. Now it's pointing here. So this is really cool, not just if you have one, but let's do like a bunch. So let's say 10. So the cone position needs to change. So let's take a radius of 5, and we'll say we'll rotate around the z-axis. Actually, let's just rotate around the z-axis. Oh no, I need I need this to be actually the right. Okay. No, I need math. So rotation around the z-axis. Here we go. Cos. Cos I times 360 over 10. Sine. And we multiply by the radius. Boom, we get all these almost like laser beams. Let's make this a little bit larger. Say 9. And we can I can make a cool animation. If I rotate, well, that doesn't work at all. Huh, funny. Actually, I can add plus 360 times $t, and that should do the trick. This part's not strictly necessary. It's just me having fun with it. Okay, so now they're going around in a circle, but they all stay pointed at this one spot. And let me just say cos 360 times $sine t. Say at plus 5, so it's sort of centered at 5, and it will go up and down. Yeah, so now they're rotating, it's moving up and down, and they all stay pointed at the point, which is pretty cool. And maybe can add a bit of color. Over 9 minus I over 9.3. Why is that not working? Sorry. Syntax error. Oh, commas. There we go. Cool. Maybe it would be more interesting. This color scheme 3. There we go. I think that's a bit more of an interesting color scheme. And one last thing, I will just change. Can I change it? The number of things. So let's say num equals 20. This is a bit smaller. Am I missing one? I'm missing an important spot for it. I don't think so. No, I definitely am here. There we go. So yeah, that's a cool thing to play around with. I could even make this 2, and I could make this 40. So yeah, now they're all pointing at this point in particular, this point in space. Yeah, just with this this simple module here. It's a pretty cool one to play around with, and it's pretty useful. So I think that is everything for this tutorial. Thank you for watching. Hopefully it was helpful, and hopefully I'll see you in the next one.